sklearn Gaussian process kernels compound kernel. Description: the compound kernel class in scikit-learn's Gaussian process library allows you to combine multiple kernels into a single kernel, representing a more complex relationship between input features and the target variable. This is particularly useful when modeling data with multiple sources of variability or when different kernel types are suitable for different aspects of the data. Inputs. Kernel objects. Compound kernel takes one or more instances of kernel objects as input. These kernel objects represent different aspects of the relationship you want to model between the input features and the target variable. You can use different types of kernels like RBF, linear, constant, and others. Kernel weights optional if you want to assign different weights to the individual kernels in the combination. You can provide these weights as input. This allows you to adjust the influence of each kernel on the final model. Outputs. Combined kernel object. The compound kernel class returns a single kernel object that represents the combined effect of all input kernels. You can use this combined kernel object in your Gaussian process model to make predictions. Kernel weights optional if you provided weights as input. The compound kernel class also returns the weights that were applied to each individual kernel. Steps. Kernel initialization. You initialize the compound kernel object by passing the kernel objects you want to combine. You can optionally provide weights for each kernel as well. Kernel combination. Internally, the compound kernel object combines the input kernels according to the specified weights. It effectively creates a single kernel function that captures the combined effect of all input kernels. Model fitting. You can then use the combined kernel object in a Gaussian process regression or classification model. The model will fit the data using the combined kernel to learn the relationship between the input features and the target variable. Metrics. Mean squared error (MSE). This metric measures the average squared difference between the model's predictions and the actual target values. It is commonly used to evaluate the performance of regression models. Log loss cross entropy. This metric is used for evaluating the performance of classification models. It measures the difference between the predicted probability distribution and the actual distribution of classes. R squared measures how much of the variance in the target variable is explained by the model. It ranges from 0 to 1, with higher values indicating a better fit. Visualization plots. Kernel function visualization. You can plot the combined kernel function to visualize its behavior and gain insights into the relationships it models. Prediction interval plots plot the predicted values with confidence intervals to visualize the uncertainty in the model's predictions. This can be helpful for understanding the reliability of the model's predictions. Fine-tune parameters. Kernel weights. You can adjust the weights of individual kernels in the compound kernel to fine-tune the model's behavior. Experiment with different weights to find the best balance between the different kernel contributions. Kernel parameters. Each individual kernel might have its own parameters, e.g., length scale for RBF kernel. You can tune these parameters to optimize the model's performance. Uncertainty methods. Bayesian prediction intervals. The Gaussian process framework provides a natural way to compute prediction intervals, which quantify the uncertainty in the model's predictions. Monte Carlo dropout. This technique can be used to estimate uncertainty in deep learning models. You can apply Monte Carlo dropout during inference to generate multiple predictions and use them to calculate uncertainty estimates. Challenges and fixes. Challenge 1. Overfitting to the training data. If the compound kernel is too complex or has too many parameters, the model may overfit to the training data, leading to poor performance on unseen data. Sample use case that resulted in Challenge 1: a model with a complex compound kernel containing many different kernel components and a large number of parameters was trained on a small dataset. The model was able to achieve very low error on the training data but performed poorly on the test data. Fixes to Challenge 1. Use cross-validation. Divide the data into multiple folds and train the model on different combinations of these folds. This helps to prevent overfitting by evaluating the model's performance on unseen data. Regularization. Apply regularization techniques, such as L1 or L2 regularization, to penalize large model parameters, which helps to prevent overfitting. Simplify the kernel. Reduce the complexity of the compound kernel by using fewer kernel components or simpler kernel types. Challenge 2: choosing the right kernel combination. Selecting the appropriate kernels and weights for the compound kernel can be challenging. A poorly chosen kernel combination can lead to a model that does not capture the true relationship between the input features and the target variable. Sample use case that resulted in Challenge 2: a model was trained using a compound kernel that included a linear kernel and a periodic kernel, but the data did not exhibit a clear linear or periodic relationship. This resulted in a poor model fit. Fixes to Challenge 2. Domain knowledge. Use domain knowledge to guide the choice of kernels. Consider the characteristics of the data and the underlying relationships you expect to model. Feature engineering. Transform the input features to make them more suitable for specific kernel types. For example, you could apply a logarithmic transformation to features that exhibit exponential growth. Feature selection. Select the most relevant features for the model. This can simplify the task of choosing an appropriate kernel combination. Challenge 3: computational complexity. Combining multiple kernels can lead to a more complex model with higher computational costs, especially for large datasets. Sample use case that resulted in Challenge 3: a compound kernel with several kernel components was used to model a large dataset with millions of data points. The model training process was extremely slow due to the high computational complexity. Fixes to Challenge 3. Kernel approximation techniques. Use techniques like random Fourier features or Nystrom approximation to reduce the computational cost of evaluating the kernel function. Sparse kernel methods. Employ sparse kernel methods, such as the sparse greedy matrix approximation, to reduce the number of kernel evaluations required. Optimization techniques. Use efficient optimization algorithms, such as stochastic gradient descent (SGD), to speed up the model training process.